let's review for the Unit 7 Energy exam. And now what I'm going to do is make a list of words that you will need to be able to define. One of them is energy. Now, energy, and I'm not going to write all these out. I'm just going to say them out loud. You guys can. It would take too long. So, energy, right? If something has energy, it has the capacity to change its environment in some way. And if something is out of energy, if it has no energy, then it can't do anything. It can't make change. And now, energy, it can be transferred or stored. This capacity to make change in the environment. It can be transferred or stored. Now, the main way that we have that we've talked about transferring energy is work. And how do we define work? Well, work is a transfer of energy through the application of a force. And we said that work is equal to a force times a displacement times the cosine of the angle between the force and displacement vectors. Work itself is a scalar. And if you are in an advanced math class, this operation between two vectors, force times displacement times cosine of the angle, giving you a scalar, it's called the scalar product of two vectors. But that's really not necessary for what we're doing in here. Just know this definition for work. Let's see. There are other ways of transferring energy, but we're not going to. I'm not going to test you on them. But light is a transfer of energy through electromagnetic radiation. Heat, if you have a temperature difference, you will have radiation or conduction or convection, depending on what's going on there. We're going to study the transfer of energy through heating when we do thermodynamics, which is coming up. Another way of transferring energy from one place to the other is electricity. It's a flow of energy through an electric field in a wire with flowing charge and all that, and we might get to a little bit of that later in the year. But mainly what we're going to focus on in this unit is energy being transferred from one system into another through the application of a force, and we call that work. Okay. Now, we have different ways of storing energy. You can store energy in motion. We call that kinetic energy. And we derived a formula for that. I'm not going to re-derive it now, but we use the capital letter K to represent kinetic energy. And that's equal to 1/2 the mass times the velocity squared. So if something has mass and it's moving, it has energy. How much energy? This tells you how much energy. And really this derived from our definition of work. If you have a net force and you make something move, or you increase its velocity, the amount of work you do is exactly equal to the amount of kinetic energy it will get. In fact, that leads us to well, let me finish this. Another way that energy is stored is potential energy. And we've got, we talked about several different kinds of potential energy. If I pull a bow, like a bow and arrow, and I pull a bow, and that I did work against this elastic material, and I can get that energy back when I release the arrow. All the energy that was stored in the bow now goes into the kinetic energy of the arrow. So I can store energy up in any. If I pull a rubber band or a spring or any elastic, stretchy, or compressing material, you can store energy in it and use it later. Now, we're not going to really talk much about elastic potential energy for the exam. But the one that we are going to use a lot is gravitational potential energy, U sub G. And we said that gravitational potential energy is the energy stored in an object because it has height in a gravity field. Like if I hold a bowling ball over your head, that bowling ball has the potential to do work or to change your environment, right? If I release it, and lawsuits will ensue and so on. But so that's potential energy. And we said, well, what is the work that gravity can do? Well, gravity will apply a force through a distance. Well, what's the force? Well, the force of gravity is mg. And then but we said that work done by gravity is a force times the displacement. Well, what is the displacement? Well, we're going to call that the height. H is the height. And so that's your height above some reference. So usually we use the ground, but you don't have to use the ground, tabletop, or whatever. And so that's the energy stored in a gravity field. That's potential energy. Now, we have this thing called the work energy theorem. And it basically says the work done by the net force on an object will be equal to the change in kinetic energy of that object. So if I give you a net force, and that net force does some work, the result of that work is a change in kinetic energy. Right? This is K final minus K initial. So, and then of course K is equal to 1 FmV squared. So if I give you a net force, I tell you a displacement, you figure out how much work was done, you can figure out what the change in kinetic energy is, and then you can solve for velocities or whatever you're being asked for. Now let me go over an example problem that you will very likely see on the exam. One of the problems, I'm going to give you the ground. I'm going to give you a crate like this, and there'll be a force, some applied force. And this thing is going to slide on the ground. And maybe there's friction on it as well. And so I might ask you, what work are done by all the forces acting on this crate? Well, let's draw a free body diagram of the crate. I've got gravity, and I've got a normal force. And I've got this applied force, and I've got friction. And the applied force is at an angle theta. Okay. Now our displacement, I'll just go ahead and draw our displacement is right here. Right? This is our delta x. So if I go through each force, let's take a look at this applied force. The work done by the applied force is equal to the applied force times the displacement. But look, only the component of the applied force that's in the same direction as the displacement does any work. And here's that component. Look, delta x is to the right, so only the component of the force that's to the right does work. And that would be Fa cosine theta. So now I'm not giving you any numbers in here, but on the exam, what you would do now is you would plug the values in there. Now let's take a look at the work done by friction. Now these are subscripts right here, right? The work done by the force of friction. I'm not multiplying anything here. It's just, that's just the variable. Now, well, it's the force of friction times delta x times the cosine. Now, what is the angle between the displacement and the force of friction in this drawing? Let's see, delta x is to the right, but the force of friction is to the left. What's the angle between to the right and to the left? 180 degrees? Now, what is the cosine of 180 degrees? It's -1. So, when I figure out the magnitude of the force of friction in delta x and I multiply them, I'm going to get a positive value. But when I multiply by cosine 180, it's going to make it negative. So the force of friction is doing negative work. Now, is that okay? Can something do negative work? Sure. See, look. See this applied force right here? See this? Somebody's pulling on this crate. They're trying to make it go faster and faster. They're trying to add energy to the crate. So they're doing positive work. But what is friction doing? It's trying to take that energy away, that kinetic energy. It's trying to keep that crate from gaining kinetic energy. And so it's going to do negative work. Negative work is done when you extract energy from the system. And that's what the friction force is doing here. It's extracting energy from that system. And so this will be negative. Now let's take a look at the work done by the normal force. Well, it's the normal force times delta x times the cosine of, now what is the angle between the normal force and the displacement? It's 90 degrees. Now what is the cosine of 90 degrees? Nope. Try it. Cosine 90 degrees. It's 0. Did you say 0? Yeah. And I didn't hear you. You have to, hey, you got to say it loud and proud. All right. This is going to be 0. Look at this normal force. It's pointed up. It's not contributing any transfer of energy to the object if it's moving to the side. Now, if the normal force was big enough where it actually lifted the object up, then it would be doing work. But it's not. It's not. The crate is constrained to move horizontally. The normal force is a vertical force in this case, and so it's not doing any work in this problem, because the angle is 90 degrees, cosine 90 is 0. Whenever the force is perpendicular to your displacement, that force isn't doing any work. So therefore, the work done by gravity, well, that would be mg times delta x times the cosine of 90 degrees. It's also equal to 0. So gravity's not doing any work on this problem. And look, everybody look up here, because when we went through this, we couldn't really say this until right now. Look, if gravity was doing work, we would be changing the gravitational potential energy of the crate. But do you see the crate doesn't change height? If the crate isn't changing height, we're not changing its gravitational potential energy. So now, what is the net work done? The net work done is equal to the sum of all of these. So if I were to add of course these two are 0, but if I were to add this work plus this work plus 0 plus 0, I would get the work done by the net force, and that of course would be equal to the change in kinetic energy of the crate. So that would get us back to the work energy theorem. So you can do that. So there's a couple of ways of figuring out what the net work is. you can figure out the work done by every single force, and then add up all of that work. Or you can figure out what the net force is on the crate, and the net force on the crate is the difference between Fa cosine theta and the force of friction. You would add them together. Of course, they subtract because force of friction is to the left, and then figure out what that force is and multiply by delta x, and you would get the work done. And of course, I'd have to give you the mass. And don't forget, hey, the force of friction is equal to mu times that normal force. So when I give you this problem, on the test, you'll need to know, to remember that friction force. Okay. So then we're going to deal with conservation of mechanical energy. Okay, so if first of all, we have to define what we mean by mechanical energy. We define, by definition, no, this is not derived, this is defined. Mechanical energy, which we abbreviate with a capital E, is, Joshua, Alanis? This is defined to be the kinetic energy plus the potential energy. Now, this potential energy, it includes elastic potential energy. But we're not going to worry too much about elastic potential energy for the test. So we're just going to, but we are going to deal with gravitational potential. But we could have, elastic potential energy in there as well. Now, if and only if, right? If and only if the only forces doing work are gravity or springs, then E initial equals E final. Or you can go E1 equals E2 or whatever. Because, look, if a spring is doing work, then there must have been energy stored in that spring, and now it's transferring that energy into gravitational potential energy or kinetic energy. Or if the spring is slowing it down, slowing the object down, it's just turning kinetic energy into elastic potential energy. But the sum of these is staying constant. If gravity is the only force doing work, which is the problem I'm going to give you, then if gravity is doing work, then it's just taking, all you're doing is pouring gravitational potential energy into kinetic energy. Or if gravity is slowing something down, like if you throw a ball up in the air, gravity slows it down, gravity is doing negative work, taking kinetic energy away from the ball, but it's gaining an equal amount of gravitational potential energy. So if you add these, you can think of these as, remember when I had the beakers out, you can kind of think of these as being 3 beakers. And when either gravity or elastic material does work, we're just pouring, we're just transferring the energy from one container into another. Okay, so you will get a conservation of energy problem. Let's see. Oh, and then let's talk about power. I think that's the last thing. So power is equal to the rate at which energy is transferred. Energy transferred over the time it took to transfer that energy. And of course we use P equals, delta E over delta T. That's one way of doing it. Now, usually, how do we transfer energy? What's the only really computational way we know to transfer energy is work. So we can say that this change in energy, or this transfer of energy, is really work over time. But work is force times displacement times the cosine of theta, and over delta t. Well, what is delta x over delta t? That's velocity. So you can also write power equals force times velocity times the cosine of the angle between the force and velocity vector. And of course, don't forget about the units. I didn't really talk about units. Let's talk about units for a second. For work, you have newtons times meters, and that's a joule. Now, for kinetic energy, you have 1/2 mv squared, which is kilogram meter squared per second squared. But a kilogram meter per second squared is a newton times the other meter. Well, this is just a joule. And gravitational potential energy, right? That's mgh, and what is mass is kilogram, g is meters per second squared, and then h is meters, right? So you get the same kilogram meter squared per second squared, and that's joules again. So everything comes down to joules. Now, a watt for power, you have a joule per second, and we call that a watt, and abbreviate it with a W. And this is a little bit confusing because W is also used to represent work, but in this context, it's a unit, not a variable. So you'll get a power problem. So on the exam, let's sit down a little bit. Oops. So you can see the whole thing here. So I'm going to give you a problem, fairly complicated one. It's very similar to this, where I want to know can you calculate how much work is done by different forces with different angles. And then I'm going to test whether or not you can use the work energy theorem. Then I'm going to give you a conservation of mechanical energy problem. And then I'm going to give you a power problem. And that should just about cover it. So 4, maybe 5 problems on the test, but they'll obviously will have a part A, B, C on it. Okay. I'll try not to go past C. If you get to D and F, that's just not fair. Okay. Any questions? Okay. That is